do that, yes.
Yeah.
So I'd like to say good morning to all the participants, all who have joined in, and also say my thanks to CMI and to Professor Mani and to Anand, who have helped out in arranging this particular event. So let me plunge straight into the event, and I'll share a screen right now. So I hope everyone can see this. So as you can see from the title, it says Euler's polyhedron theorem and some applications. Euler was one of the very great mathematicians of all time, with perhaps a larger number of publications than almost anybody. And you will find his name associated with just about every possible area of mathematics. So we are going to be looking at a particular theorem of his, for which holds for convex polyhedra. Well, I'm going to be describing the theorem, so I won't say anything more about it now. And I'm also going to be describing a somewhat lesser known result first found by the philosopher mathematician Rene Descartes. And it turns out that it is closely related to Euler's theorem. It is much less known. And after that, I'm going to describe a few applications of Euler's theorem. So here are the two people concerned. As you can see, Leonhard Euler lived mostly in the 18th century, 1707 to 1783. And Descartes was very much earlier, 1596 to 1650. And Descartes, I'm sure all of you will know, is associated with coordinate geometry, but with many other things as well. So the story has two starting points. First, let me say what happened in 1750. Leonhard Euler announces his polyhedron formula, in which he announces a connection between the number of vertices, the number of edges, and the number of faces of any convex polyhedron. When I say announces, Euler was in the habit of announcing most of his results in letters that he wrote to his friends and companions. And more than a century earlier, there was Rene Descartes, who communicated a result concerning what he called the total angular defect of a convex polyhedron. So I'm going to describe these two terms very soon. So let me explain the term angular defect, because it's not probably very familiar to most people. Here I show a cube. Now a cube, as you know, is made up of squares on all its sides. Imagine at a corner, you cut out all the squares. There are three squares meeting out here, and you arrange them like this. Now, naturally, you will notice that there is a gap left in the corner here, right? It's because each of these is a 90-degree angle, and the three 90-degree angles add up to 270 degrees. So there's a gap of 90 degrees left out here. That gap is called the angular defect. And if you do the same thing for a regular tetrahedron, you have three faces meeting at a point. All three are equilateral triangles. So all these angles are 60 degrees each. And if you were to cut out the faces and lay them out together, at one particular point, meeting at one point here like this, you'll notice that there's a big gap left on the other side. And these three add up to 180 degrees. So there's a gap of 180 degrees. So the angular defect here is 180 degrees, which you'll notice is very much more than the angular defect here. And Descartes was the first, perhaps, to realize that this is also a way of measuring the curvature. All of you will agree that this particular vertex, this point, seems somehow more sharp, more pointed than this point. And it's obvious that the angular defect, the larger the angular defect, in a way, the more this is pointed. So it's a good measure of curvature. And what he found was something quite remarkable, as we'll see now. Let's take the case of a regular tetrahedron. And this is what I'm going to do now is to go through a series of exercises, and we'll sort of discover the two theorems bit by bit. So first of all, let's take a regular tetrahedron. It has 4 vertices, 1, 2, 3, 4, 6 edges. You can't see all of them, 1, 2, 3, and 4, 5, and the 6th one is behind out there. And of course, it has 4 faces, 1, 2, and there is one behind and one underneath. So 4 faces. So you have V equal to 4, E equal to 6, and F equal to 4. And you notice this relationship. v minus e plus f works out to a figure of 2. Probably many of you have heard of this result. It's known as Euler's theorem. But the next part may be less familiar. Let's look at the angular sum at each vertex. Now, we just saw for a regular tetrahedron that the angular sum at each vertex, will look at this vertex here. There's a 60 degree here, 60 degree here, underneath 60. So it adds up to 180 degrees. So there's an angular defect associated with this vertex of 180 degrees, right? And the same is true for all 4 vertices. So the total angular defect is 4 times 360 minus 180 degrees, which comes out to be 720 degrees. I hope that is clear. Now, keep in mind this figure of 720 degrees. Make a mental note of it. Let's go to the case of a cube, which is also known as a hexahedron. Just like a tetrahedron has 4 faces, a hexahedron has 6 faces. Let's look first at the Euler part of it, the V and the E and the F. It has 4 vertices on the top, 4 at the bottom. So it has 8 vertices altogether. It has 12 edges. You have 4 at the top, 4 at the bottom, parallel to these 4, and then 4 vertical. So 12 edges altogether. And it has 6 faces. You can see 3 of them here and another 3 in they are back, 1 below, 1 this side and 1 this side. So F equals 6. And if you work out the value of V minus E plus F, once again, you get this figure of 2. Now let's look at the angular defect. Now here you have at each vertex 3 90-degree angles meeting. Right? We saw that just a moment back. Look at this vertex. You have 190 degree here, a 90 degree here, and underneath another 90 degree. So the angular sum comes out to be 270 degrees. So the angular defect at each of these vertices is 90 degrees. 360 minus 270 is 90. And since there are 8 vertices, so the total angular defect comes out to be 720 degrees. And remember, last time also we got 720 degrees. Now this is quite curious. Let's look at the case of a regular dodecahedron. Slightly more involved computations here. First of all, even figuring out the vertices takes a little bit of thought. You can see that there are 5 vertices on top and similarly 5 down here. And sort of in this zigzag pattern around, there are 10. So there are altogether 20 vertices. And if you count carefully, you'll find it has 30 edges. It's an interesting mathematical task to figure out the number of edges without actually counting them 1, 2, 3, 4, and so on. Actually, to figure out that there are 30 edges and 12 faces. Perhaps you could try it out yourself. And if once you do this, you find that V minus E plus F comes out to be 20 minus 30 plus 12. And that works out to 2. Yet again, it is a 2. Now let's look at the angular defect. Now here, each face is a regular pentagon. Now what's the angle of a regular pentagon? Each of these angles is 108 degrees, right? Each angle of a regular pentagon is 108 degrees. So there are 3 such vertices, 3 such angles coming together, and the total angle adds up to 324 degrees. So the defect is only 36 degrees now, 360 minus 324 degrees. You'll notice it's a fairly small quantity, 36 degrees. And that fits in with our intuitive understanding that this has much lower curvature than, say, the case of a regular tetrahedron. It's much less curved. Anyway, so you have this 36 degrees, and there are 20 vertices. So 20 times 36, yet again, you get 720 degrees. So we'll just look at one more such case, which is the case of a regular icosahedron. And here also, it's a very interesting task to figure out the number of vertices, edges, and faces without actually counting them 1, 2, 3. So here you have this kind of a top, which is sort of, it comes at the top of this object. And similarly, symmetrically, there's another object, a kind of this is like a hat, and there's the mirror image of the hat coming underneath. And like an equator, there's a band around it. So you get these 12 vertices, 1 at the top, 5 here, 5 here, and 1 down below. So 12 vertices. If you count the edges, you'll get 30. and there are 20 faces. In fact, some of you may know that this figure, this object, is very closely related to the dodecahedron. You'll find that these figures are very, you'll be reminded immediately of the dodecahedron. So if you work out v minus e plus f, you get 2 yet again. And let's look at the angular defect here. Now each face is an equilateral triangle, a lot of 60-degree angles. So here you find 5 60-degree angles meeting at a point. So if you add up these angles, you get 300 degrees. That means the angular defect is 60 degrees at each vertex. And since there are 12 vertices, you get 12 times 60, which is yet again 720 degrees. So now you begin to see enough cases of this kind, enough to generalize. And you can actually now guess the theorems. So these are two very great theorems which have come down, have become classical theorems of the field. So one is the theorem of Rene Descartes, that the total angular defect of a convex polyhedron is 720 degrees. And Euler says something very similar, that if V and E and F are respectively the number of vertices, edges, and faces of a convex polyhedron, then this quantity is invariably equal to 2. And some of you may notice, your ears will pick up that this 720 degrees is exactly twice of 360 degrees. And it turns out that, that is not a coincidence. These two theorems are in fact actually equivalent to each other. If you assume Euler's theorem, you can prove Descartes' theorem. And if you assume Descartes' theorem, you can prove Euler's theorem. And I'd like to just say one thing before we move on to the applications. I'm going to show you some interesting applications immediately after this. The first is, everywhere I have been saying convex polyhedron. Now, what does convex mean? If you look at, say, a figure like this, the previous slide, it's convex in the sense it has no indentations going inside. All of you know probably what is a non-convex quadrilateral. I've not got a figure of it here, but maybe I'll draw it on the board later. And similarly, you can have non-convex, various kinds of non-convex figures. So here we are making use of the fact that it is convex. But actually, both these theorems are true for slightly broader class of objects than convexity. All that you need is that you need a polyhedron which is sort of well-behaved and doesn't have any holes. Something that if it were made of clay or plasticine, you could sort of mold it and make it into a sphere. Both these theorems are true slightly more generally, but we need not go into all that. So that's why I kept saying convex polyhedron. We don't need to take all those special cases. And this other comment which I'd like to say is that this theorem may remind you of something which is there in ordinary plane geometry, which is if you take a convex polygon, the sum of the exterior angles is always 360 degrees, which means 360 degrees is a kind of constant. For every convex polygon, you get exactly the same figure. So this is also something very similar to that. There is a kind of invariance out here. And it turns out that this has an interpretation which is not just in terms of degrees. It's like adding up the total curvature of this object. But we won't be going into all that right now. So I'm going to be showing you a number of applications where the applications are basically actually of Euler's theorem. We are not going to be looking again at Descartes' theorem. So let me say, first of all, that Euler's theorem, the way I defined it, you may get the impression that it is basically about polyhedra, but actually it's only incidentally about polyhedra. In fact, when Euler initially proved it, he proved it for polyhedra, and he may or may not have realized that the theorem is true more generally. It's not just true for polyhedra. In fact, it is true for what is known as any network. And let me give an example here. Let's take this drawing out here, where I have a number of points which are called vertices. The vertices are joined together by edges. And as a result of joining the edges, they create certain regions which we call faces. very much like the faces of a polyhedron. So if you look at this whole object, and this outside face is also counted. So here you have, for example, 4 vertices, 5 edges. You can count 1, 2, 3, 4, 5 edges, and 3 faces. Why 3? 1 here, and 1 outside. And if you look at these figures, 4, 5, 3, you'll find that v minus e plus f once more is equal to 2. Let's look at another graph or another network. Here you have 1, 2, 3, 4, 5, 6 vertices. The number of edges is 1, 2, 3 here, 1, 2, 3, and there's one more here. So 7 edges. And finally, the faces are, there's 1 here, 1 inside here, and 1 this outside. So basically the faces, you can think of the faces as, imagine that these represent knife cuts. So into how many pieces is this entire plane divided? So similarly, when you sort of cut along these, just along these, you'll get 1 piece here, 1 piece here, and the rest of it remains in 1 piece. So once again, if you look at these figures 6, 7, and 3, you again get this figure of 2. And similarly here, much simpler case, you have here how many? 1, 2, 3, 4, 5, 6 vertices. There are 1, 2, 3, 4, 5, 6 edges again, and 2 faces, 1 inside here, 1 outside. So 6 minus 6 plus 2, once again you get 2. And though this is not going to be the focus of my talk, I'll just show you how you can actually prove Euler's theorem. Once you realize that Euler's theorem is not just about polyhedra, but also about networks. And from networks, you can go back to polyhedra. It turns out it is much easier to prove it for networks, for graphs. And I'll show you for how you can do it. All of you, I'm sure, are familiar with the idea of induction. So here we've taken the first graph, which was there on the previous page. This one, which has 4 vertices, 5 edges, and 3 faces. Now, I do a transformation to this graph by removing the central, this edge here. Now, what happens when you do this? By removing this edge, the vertex count does not change. You have 4 vertices here, 4 vertices here. All you have done is remove an edge. So you've still got 4 vertices. The edge count, however, has gone down by 1. Earlier you had 5, now you have 4. And of course, the face count also has gone down by 1 because these 2 faces, which were separated by this edge, have now got merged together. So both E and F have come down by 1. Since both E and F have come down by 1, if you look at this quantity V minus E plus F, it doesn't change, right? Because both of them have come down by 1. Now let's remove one more edge. Let's remove, say, this one. Now you get this figure out here. Again, the vertex count has remained the same. It's still 4. Edge count has again come down by 1. From 4, you've got 3 because you lost this edge. And the face count also has come down by 1 because these 2 faces now have got merged. So again, V minus E plus F remains the same. Now you can't do that kind of operation anymore because there's only one face left. So let's start removing edges together with a vertex which is left all by itself, a lonely vertex. So we remove this edge here along with this vertex. So now the vertex count goes from 4 to 3. It's only 3 here. So it has come down from 4 to 3. And the edge count also has come down by 1 because it was 3 edges and now it has become 2. And the face count has remained the same. F is still 1. So since V and E both have come down by 1, V minus E remains the same, which means V minus F again remains the same. So you do yet again the same operation from here to here. You remove one, in this case, we remove this horizontal edge. So V comes down by 1, E comes down by 1, F remains the same. Again, V minus E plus F remains the same. And finally, you're just left with this situation where you have removed everything except just this one vertex. You have V equal to 1, E equal to 0, and F equal to 1, for which, of course, V minus E plus F is equal to 2. So by this kind of a procedure, any connected figure like this, you can ultimately reduce it to a single vertex, for which V minus E plus F obviously is equal to 2. So that's, in a way, showing you how Euler's theorem is proved. So as I mentioned earlier, it's I'm not going to prove Descartes' theorem out here. I'm not going to show you how you can go from Descartes to Euler or the other way around. I'll leave that to you as a kind of homework. So just to show you the connection between the two, look at, say, a figure like this. You have a sphere covered with polygons so that every part is enclosed in a polygon. In this particular figure, everything is enclosed in a hexagon, but that hexagon and pentagon, sorry, this is the football kind of figure. It's called the truncated icosahedron. But doesn't matter about that. But you can imagine by pumping this up, thinking of this as a balloon, you can pump it to the air and make it round like a sphere. And you can then think of it as a network. And then this V minus E plus F equals 2 applies to that. And that's how the connection with polyhedra comes. So now I'm going to move away and I'm going to show you 4 very unusual applications of Euler's result. All right, so here they come. Let's start by talking about the Venn diagram. All of you are familiar with Venn diagrams, but you may not have guessed that the humble Venn diagram holds within it a very interesting combinatorial problem. And that comes about like this. All of you are familiar with the idea of representing sets using shaded disks. For example, if you have a single set enclosed within the universal set, this is how you show it. And if you have 2 sets, this is how you show it. Now, why is this okay to show it? Because if you have a single set within a universal set, if you take any element of the universal set, it can be thought of as it should either be in that set or not in that set. So that there are only 2 possibilities for that element. And there are 2 regions here. So there's a single set and 2 regions, and there are 2 possibilities for each element. So you'll notice that the numbers match. You have 2 regions and 2 possibilities. Let's look at the case of 2 sets. You'll notice that they intersect in a certain region. So they divide the space into 4 regions, one outside here, one in A alone, one in B alone, and one which is enclosed in both A and B. And now let's look at individual elements. Now, since there are 2 sets, it can be thought of in like a binary number with A and B both as the coordinates. It could be in A and in B. It could be in A and not in B. It could be not in A but in B. And it could be not in A and not in B. You'll notice that there are 4 possibilities. I hope you got that. So there are 2 possibilities for A. It's either in A or not in A. 2 possibilities for B also, not in A, B or in B. And therefore 4 possibilities altogether. So you'll notice 4 regions, 4 possibilities. So this Venn diagram is accurate. In the case of 3 sets, again, this is a very familiar looking figure. You study it probably in 7th or 8th standard. Now there are 3 sets. So you get 8 possibilities, which is 2 cubed. Right? In A or not in A, in B or not in B, in C or not in C. So 2 times 2 times 2, which is 8. And you'll find that there are 8 regions here. You'll just count them out. The numbers again match. But now if you you'll notice that in the school books, we never look at the case of 4 sets at all. And here you'll see why. What happens with 4 sets? Since there are 4 sets, there are 16 possibilities, right? Because in each of the sets, it can either be there or it can not be there. So 2 times 2 times 2 times 2, you get 16 possibilities. But if you look at the Venn diagram, you run into a difficulty because here I have shown a situation where you have 4 overlapping circles. Every 2 of them do intersect. We don't lose any regions. But if you carefully count all the regions, you'll find you get only 14 regions out here. The numbers do not match. Now, you might wonder whether we have just been rather clumsy in drawing these circles. Maybe there's another way of drawing it so that you get 15 regions or 16 regions. Now, I'm going to ask that general problem. Suppose you have n circles drawn out here, not 4, but n circles, and every 2 of them intersect. How many regions are you going to get? So this is a very interesting problem. So let's look at it here. So now look at this general figure. Suppose a point like this where 2 circles intersect, we call it a vertex. The region between two vertices, we call it an edge. So it's like each, say something like this is an edge. Now this picture is a network, is a graph. So again, Euler's theorem must apply. V minus E plus F is equal to 2. And we want to have maximum possible number of regions. So also you don't want 3 circles to concur. Hello, just a minute, please. I think I lost connectivity. Just a minute, please. I'll just get back my screen.
Hey,
just a minute, please. Just a minute. I seem to have lost connectivity. Hold on, please. Connectivity gone. Yeah. Hello.
Yes, you are connected. You just have to share your screen, I think.
Oh, okay. All
yeah.
Right.
Yeah, we can see your face, but not the screen. That's it.
Okay, all right. So now,
perfect.
I think I'm not sure where you lost me. Somehow I saw the screen suddenly fading away.
Yes, so maybe you could probably begin with the slide. Probably that's the easiest since it's very difficult to know.
Yeah, I'll just say again what these things mean. So this can be thought of as a network, and each intersection here I count as a vertex. So there are V vertices. Each of these portion which connects two vertices, I think of it as an edge, and each such region like this I count as a face. So V minus E plus F, of course, is equal to 2. Intersect each other, and no 3 circles are concurrent. Now I'm going to use a simple counting principle. Remember that 2 circles intersect in exactly 2 points, which means that the number of vertices must be twice n choose 2. Because there are n circles, so n choose 2. So you get n, and you know that n choose 2 is n times n minus 1 upon 2. So that means V comes out to be n times n minus 1. I hope you have got that. Now to figure out, so we have this simple argument has given us the value of V. Now to find the value of E, and initially it looks quite complicated, but there's a simple way of doing it. Look at this way. Go to any vertex, you will find that there are exactly 4 edges coming out of it. For example, they are here at the bottom. There's one vertex, one edge going here, one this way, one there. And that's true of every single vertex. Which means that if you visit vertex by vertex and count the edges going away from it, since every vertex has got 4 edges, you will get a count of 4 times V, right? You're visiting V edges, each one has a count of 4, so you get 4 times V. But now every single edge will get counted twice. For example, this particular edge will get counted when you come to this vertex, and it will get counted again when you come to this vertex because it connects these 2 vertices. So the same count on the one hand is equal to 4V, on the other hand it is equal to 2E, which means that 2E is equal to 4V, and that gives you a value of E. So that's a very nice argument to get E. So we have just worked out V is equal to n times n minus 1. We have also worked out E is equal to 2V just now above. So from combining these two, you will just get E is equal to 2n times n minus 1. So we've got V, we've got E, and we've got also this relation, V minus E plus F is equal to 2. So from this solving for F, you get F is equal to E minus V plus 2, taking everything that side, which means it is N times N minus 1 plus 2. So this is a very nice result that you have got the maximum number of regions that you can create using N circles is N squared minus N plus 2. Note, now if you actually calculate the values of this for N equal to 1, this is 1 squared minus 1 plus 2, which turns out to be 2, as we know. If you take N equal to 2, you will get 2 squared minus 2 plus 2, which is 4. Again, it fits in with our experience. For 3 circles, it is 3 squared minus 3, which is 6, plus 2, which is 8. Again, fine. But with 4 circles, you get 4 squared minus 4, which is 12. And 12 added to 2 is 14. So you see, we don't get 16. And for 5, the discrepancy is even more. 5 squared minus 5 is 20. 20 added to 2 is 22. So it's quite interesting that this approach, this Venn diagram with circles, works only if you have 3 or fewer sets. It doesn't work with 4 or more sets. So now let's go on. All of you must have seen this, wondered about this problem. Supposing you have a pizza. Pizzas are typically round. You are allowed to cut it with n times with straight cuts. You know what's known as a pizza cutter. You just run it n times through the pizza. What is the largest number of pieces that you can get? We'll call it R of n. So let's try to solve it. So if you have just a single cut, obviously you get 2 regions, 2 pieces. I call them regions in conformity with the Euler's theorem. If you have 2 cuts, I get 4 regions, 2 lines, 4 regions. So I get R of 2 is equal to 4. If I have 3 cuts, if you make a careful count here, 1, 2, 3, 4, 5, 6, 7, you get 7 pieces. Now, can you find a general formula for Rn in terms of n is the question. And I'm going to use exactly the same kind of argument to get it. So what are we going to do? So this is the general picture. It's just supposed to represent the pizza, the round shape, and there are n lines through it. We're going to assume that every 2 lines intersect at some interior point. Like, for example, these 2 intersect out here. We don't want them to say 2 lines intersecting at the boundary. Because if they intersect at a boundary, you're going to lose a region. Similarly, you don't want 3 lines to be concurrent, because if that happens, again, you will lose a region. So once again, like in Euler's theorem, we'll let V be the number of points of intersection inside. That includes, by the way, these outer points also, that they are also part of the graph. Not only the ones which are inside, but the ones on the boundary. E is the number of edges, and R is the number of regions or pieces which it is cut into, all these pieces. And we're going to find R, and the formula we're going to use is V minus R is equal to 1. This time we won't put it as 2. Why not? Because the region outside is not being counted. Otherwise, if you were to count, if you were to apply Euler's theorem in the usual form, there's also an outside region. So it's only equal to 1. So let's see how to get, so it's R that is not known. That means we must get V and E somehow. So let's see. Now V can be obtained by a very nice and simple argument. Every 2 lines intersect, right? There are n lines. So you get n choose 2 intersections, which are inside here. Because there are n lines, every 2 of them intersect. Also, every line, let's take this line, for example, it cuts the outer circle at 2 points, this point here and this point here, which means since there are n points, there are 2 n points which are distributed around here. 2 for each line, so 2 n points. And since there are 2 n, they divide the circumference into 2 n pieces. So there are 2 n arcs on the outside here. So the total number of total number of vertices, sorry, I was counting vertices, is n choose 2 plus 2n. So 2n from these here. Number of edges. Now let's see how to get the number of edges. This is an interesting problem. let's look at any particular, for example, let's look at this here. In this picture, there are four lines which have been drawn. You'll find that each one has been divided into four pieces, right? Because each one cuts the remaining ones. So that means, and there are n such things. So that means the total number of pieces that you get is n squared, right? So for example, this one, it is 1, 2, 3, 4, and 4 for all of them. So you get 4 times 4, which is 16. So from the straight cuts, you get n squared pieces. And what about from the circumference of the circle? As I pointed out, there are 2n points on the circle. So they create 2n arcs. So the total number of edges is n squared plus 2n. So finally, we have r is equal to e minus v plus 1, which means it is n squared plus 2n, subtract n choose 2 plus 2n, the 2n cancels out. So you get n squared minus n choose 2 plus 1. And if you simplify that, you get this simple, nice expression here. Half of n squared plus n plus 2. That's the answer in this case. So again, this is a nice application of Euler's theorem. Some of you may try to get the same result in some other way. And of course, there are other ways of getting it. Now, the next problem I will consider is an interesting problem of cartography. Now, let's look at a situation like this. Here you have a square grid. Those of you who remember your atlases from your school days, from your earlier classes, will remember that you'll find these rectangle, the whole map of the world represented as a rectangle, which is divided into a grid like this. And of course, you may have also seen pictures of the globe which look like this, where you see this grid covering the whole globe. And you may wonder, so I'm just wonder out here, is it possible to completely cover the globe with a square grid? Exactly like this grid. Can you have a grid like this which covers the entire globe? Now what is shown here does not work because while out here it looks fine, there's a problem out here. You find too many points meeting at, too many lines meeting at a point, right? So what we want is every face should be bounded by exactly 4 edges. In other words, this should be uniformly covering the whole globe. Is that possible? And every vertex should have degree 4. So let's see if that is possible. Well, suppose it is possible. We are going to now try a proof by contradiction. So let the grid have V vertices, let it have E edges and F faces. Now this is just the representation. It's supposed to be covering the sphere. Then of course you have V minus E plus F equal to 2. Now, by a familiar argument, I'm going to now say that since every vertex, you have 4 edges coming together at that point. Every single vertex has 4. When I say degree 4, it is like in chemistry, you have valency. You have 4 edges meeting at every single point. So that means if you visit each edge and count the number of edges going away from it, you'll get 4 times the number of vertices, right? 4V. And just like I pointed out earlier, each edge has got 2 vertices at its ends. So each edge gets counted twice. So that same count will give you 2E. So 4V is equal to 2E, which means V is equal to E upon 2. And in the same way, if you go from face to face to face to face, each face is bounded by 4 edges. So if you count, you'll get 4F is equal to 2E. Right? For each face, you get a 4, so 4 times the number of faces. And each edge is shared by 2 faces. This is a crucial point, that each edge is shared by exactly 2 faces. So again, if 4F is equal to 2E, so you get F is equal to E by 2. And now you have a very simple conclusion. You have, if you calculate the quantity V minus E plus F, you will get V was turned out to be E by 2. F also turned out to be E by 2, and so you get E by 2 minus E plus E by 2, and that comes out to be equal to 0. So there's no way it's going to come out to be equal to 2. So that means this relation cannot possibly hold. And so you see this is an impossible configuration. So we have a sort of combinatorial proof of something which intuitively you may have realized should have been true. Now, for the last application that we will see, I'm going to look at a slightly tougher problem about chords in a circle, and it features a very famous sequence with a very misleading pattern. So once again, all of them you'll notice are of a similar kind, of a counting kind. So what I'm going to do here is I'm going to mark n points on the periphery of a circle. And then I draw all possible connecting chords. So you have here, I have just 1 point. So well, there's no connecting chord at all. Here I have 2 points. So there's a single chord. Here 3 points. So when I draw all the chords, I get this situation here. And in each case, I'm going to count the number of regions. So here there's a single region. So I'm going to write f of 1 is equal to 1. Here I get 2 regions. So I write f of 2 is equal to 2. Here I get 4 regions. So f of 3 is equal to 4. Let's look at the next case. If you put 4 dots, 4 points on the circle and join everything, you will find you get 8 regions. 1, 2, 3, 4 on the outside and 1, 2, 3, 4 out here. So 8 regions altogether. If you put 5 points like a pentagon structure here, I leave it to you to check that there are 16 regions out here, or we can do it. So there are 1, 2, 3, 4, 5 on the outside. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 plus 5 is 16 altogether. Now, what about the case of 6? You'll notice that unlike the case of 1, 2, 3, 4, I have drawn a slightly irregular kind of figure here. And that's because if I were to put 6 dots in a symmetrical way around here, you will find that 3 lines, 3 chords concur. So you lose a region. And we don't want to lose any regions. So that's why I made it slightly irregular to get the maximum possible number of regions. So the question is, what is this number for F6? So we have got the first 5 numbers as 1, 2, 3, 4, 5. 1, 2, 4, 8, 16. And surely you would expect that the next number is going to be 32. Well, it turns out not, but it's a very surprising thing how. So let's see how to analyze it in general. Here, the reasoning is slightly more sophisticated, so please listen very carefully. Once again, you imagine a situation like this, where you have V vertices, E edges, and F regions. And once again, V minus E plus F is not 2, but 1, because we are not counting this outside region. Now, what we want to do is we want the value of F. So somehow we have to get the expressions for V and E in terms of the number of points. To get V, we look at the fact that there are 2 kinds of vertices. There are border vertices, which are on the circumference of the circle, and there are interior vertices. Obviously, the number of border vertices is n, because we put n dots on the south. To get the number of interior vertices, you use a very clever argument. I claim that the number of interior vertices is actually n choose 4. And this looks like a very unintuitive result, but you realize that every interior vertex corresponds to 2 diagonals. For example, let's look, I'm sorry, I have not drawn a separate figure for that, but just imagine, let's say this chord here and this chord here, they meet out here corresponding to, and the meeting point of these 2 chords gives you 1 interior vertex here. So this interior vertex corresponds to choosing these 4 points, right? So choosing any 4 points on the circle, it's like choosing a quadrilateral, and by drawing their diagonals, you get exactly 1 point inside the quadrilateral. So each interior point corresponds to a choice of 4 points on the outside. So you get this n choose 4. So n choose 4 is a count of the number of interior points. Now, so we have managed by a clever argument to get V. And how do you think we'll get E? E looks initially a bit of a nightmare, because you'll find that some chords are connected into less number of pieces. For example, this chord is not connected into more pieces at all. And here you have a chord connected into 1, 2, 3, 4 pieces. and some 1, 2, 3, 4, 5. So they are divided into different numbers of pieces. So that argument will not work. But the degree argument will work, because each interior vertex, once again, has got 4 edges coming out of it. So it has degree 4. Now let's look at the border vertices. What will be each border vertex? Each one of them, let's look at, say, this one here. There are n vertices altogether out here. So this is connected to each of the other n minus 1. So the number of edges coming out from here is n minus 1. So it has degree n minus 1, and then it has 2 edges coming out from here. So n minus 1 plus 2, which gives you n plus 1. So each of the border vertices has got degree n minus 1 plus 2 or n plus 1. So each of these has degree 4, and we just found out that there are n choose 4 of them. So if you go to each such vertex and count out the edges, you'll get 4 times n choose 4. And if you go to each border vertex and count out the edges, we just saw that the degree is n plus 1, and there are n of them. So you get n plus 1 times n. So exactly like earlier, so if you add these two together, you're going to get twice the number of edges. So E is half of this, which means E is 2 times n choose 4 plus half of this. And a simple algebra will show you that half of this is just equal to n choose 2 plus n. So E is equal to this figure. And so since EF is equal to E minus V plus 1, we've already got E. E we had found is this, and V was this. So if you work out the algebra, you get this truly beautiful result that the number of regions when there are n points is exactly equal to n choose 4 plus n choose 2 plus 1. And if you want to put this in a more symmetric way, you can express the 1 as n choose 0. So you'll get this very nice looking expression, n choose 4 plus n choose 2 plus n choose 0. And what is interesting is if you actually work out the value of n choose 4 plus n choose 2 plus n choose 1 for 1, 2, 3, 4, 5, 6, 7, well, for up to n equal to 5, you just get the sequence of values which we had worked out. You get 1, 2, 4, 8, 16. But for 6, you get 31, not 32. And for 7, you get 57. So the shortfall from 64 is even more. So mathematicians have sometimes amusingly called this the law of small numbers. What does that mean? Sometimes the initial values of a sequence can deceive you. By looking at 1, 2, 4, 8, 16, we'll say, that must be the sequence of powers of 2. But it turns out to be not the case at all. It is an entirely different sequence, but a very much an extremely beautiful pattern here, this formula. Okay, so I have reached the end of my presentation, and that's all I have for you. So thank you for listening, and I'll stop the sharing right now. And I hope you will ask questions now.
Thank you very much, Dr. Sahyadri. It was a wonderful talk. So many beautiful applications. It's really wonderful. Now, there is a form, Google form for feedback, which will be put up, and it will be there for about 2 minutes. After that, you can start the question answers, put in the Google form, and the question answers will be given to Dr. Sahyadri, and he has kindly agreed that he will respond to those. You will be able to see it in the Google form. I request you to read it out so that we can all hear it once. Yes. So the 2 minutes is starting now. So in another 2 minutes, please fill up the feedback. It will be very useful to us for future arrangements that we are planning. Incidentally, the next talk is going to be on Higgs boson and more recent developments. And it will be by Professor James Libby of IIT Madras. And the next one will be on Science of Music by Susan Konar of NCRA Pune. So, and these are the next 2 talks, which anyway, you will all get the link. Thank you. Again, please do fill up the feedback form. It will be very useful to us. Thank you again. As they're filling the form, can I ask you one question? Dr. Sahyadri.
Yes, please, of course.
If I take a sphere and draw various circles, not necessarily great circles, but circles, how many pieces can I get as that? How many regions can I make?
We should be able to work it out exactly this way, because every two circles will meet in now in 4 points. Sorry, 2 points. We have a situation where two circles meet in two points. Actually, it will be very similar to the situation for a plane, because you can imagine it's like a stereographic projection onto a plane. You can get back the circles here. I'll have to work out the result, but it seems that you will get exactly the same answer as for the Venn diagrams, seems to me. Let's see. N-dimensional shapes.
It looks like a tacklable problem, yes.
Yeah, that's right. I'm sure we can do it by much the same approach. So please let me know when I should respond.
Yes, sir, we'll do that. This is to all the participants. There's a feedback form. Kindly fill that. Thank you. After which we will share a form. Okay, it looks like it's already been shared. Right. All right. Shirali sir, you can open that Google Forms if you want now.
We have, in fact.
Are the responses coming in?
Yes, I've got 5. I can see 5 responses till now.
Good. So then you can get started, sir.
Okay.
Yeah.
Not
if you can share your screen also, so we can also see the questions.
Oh, I see. Just a minute. Okay. Oh, what happened to it? Just a minute.
Yeah.
Can you see it?
Yeah, we can see. We can see your screen. Yeah.
Yeah. Yeah, not all of these are so easy to answer, but let's look at, for example, this second one. It should be possible to answer this. Now, it turns out that for objects having holes like a donut, or what is known as a torus in general, I'll draw it on the board actually. So the Euler characteristic V minus E plus F, we had got the value 2. But if you have a polyhedron which has a hole in it, it turns out that it is not 2, it's going to be less than 2. And if it has a single hole, it turns out to be 0. And this is, in fact, I have drawn it right before the presentation. If you look at this particular case, it becomes very interesting. This is out here, imagine a solid block with a hole drilled through it. So what is V, what is E for, and what is F for this? So V is 4 and 4 and 4 and 4, it's 16. And what's E? There's 4 on the top, 4 at the bottom, 4, this 4, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 12, 24, and 4, 20, 28, no, and for 32, yeah, 32. If you carefully count the edges, you'll find there are 32 edges, including the ones which are hidden. And the number of faces, let's see how much is. You have 4 around here, 4 at the top here, similarly 4 at the bottom, and then 4 inside. So you get 16. So you'll notice V minus E plus F is 0. So when you have a single hole, the Euler characteristic of such an object turns out to be 0. And it's interesting to look at the angular defect also. For example, let's look at this situation here. If you look at these vertices, they are just like cube. So the angular defect is 90 degrees, right? They're same as a cube. So there are 8 of them. But let's look at this. Something very surprising happens at this kind of a vertex. It's a bit difficult to imagine, but it's got a plane surface this way and a plane surface this way. So there you get 2 90-degree angles. So you get 90 degrees plus 90 degrees. And then these 2 angles, this around it, it's obviously you're losing 90 degrees. So you get 270 degrees. So very strangely, if you add up all the angles of corresponding to that vertex, you get something more than 360 degrees. So the angular defect comes out to be negative 90 degrees. So since there are 8 such vertices, 1, 2, 3, 4, and bottom 8. So you get 8 vertices with an angular defect of minus 90 degrees. and 8 with a defect of plus 90. So the total defect comes out to be 0, very strangely. So exactly it corresponds to this. So you can actually have an extension into higher objects with holes. And this is an example. And if you have one more hole, it will further bring down the Euler characteristic by 2. So that would be answering your question. This question here, can Euler's theorem be used for this? And what happens? Yeah, this question also, when there are holes. Let me see. Now, many of you asked questions about extending this to 3 dimensions. Now, this is not, it's not so easy to extend this kind of a reasoning to 3 dimensions as far as I can see, because, let's see, if you try to, for example, say you have n planes. If you have n planes, and how many regions are they going to create? It's like slicing space with n cuts. How many regions are you going to get? Can you get that count using the same kind of a reasoning? I think this will have to be given some thought. I don't have an immediate answer to that. I suspect that the answer is no, but let me think about it. All right, I'll perhaps post an answer which for you. Some of you have said, what are some good resources to learn this knack of making combinatorial calculations? Well, there's nothing very special about it, but combinatorics really come, you get a feeling of intuition for it when you study these kinds of systems and you look for symmetries. All these very strongly made principle of symmetry. For example, you had a situation where each vertex had 4 edges emanating from it. So that's very important that there's a figure of 4. So you're making use of symmetries of that kind. So whenever you look for symmetries and you find some general thing which pattern which exists all through the objects in that set, it allows you to use combinatorial arguments. If you have something which is very irregular, then combinatorial arguments are not going to work. Can the final proof of regions in a circle created by chords be extended to 3 and higher dimensions? So what does that mean? Let's say 3. Don't go to higher dimensions. Let's say you have a sphere. In this case, it's not clear how, in what way you're going to extend the problem itself, because the problem does not extend in such an easy way. In the case of the way we were looking at it, you put n points on a circle and drew all possible chords. Now, in what way are you going to extend this to 3 dimensions? Because if by drawing chords within a sphere, there's no guarantee that the chords will even intersect each other. However, you can instead choose 3 at a time. Yes, so we could make up some kind of a problem from that. Take all possible combinations of 3 points, draw planes connecting those, passing through those 3 points, and then trying to work out how many regions are going to be created. I'm afraid I have not solved that problem. It sounds like a very fascinating problem, but I have not solved it. So let's keep these as, I think these are all sources of further inquiry rather than, I won't be able to answer them offhand like this. So now in here, one of you has asked, in the map application, you showed the vertices at the ends don't give rise to 4 edges because the map is not connected. Well, basically what it shows is that you can't have this kind of a symmetric figure extending all over the globe. At some point, there's a problem. In this case, the problems happen at the in the usual kind of a way that you draw the grid over the Earth. The problem happens at the North Pole and the South Pole, right? You have all the longitudes meeting at that point, so you don't no longer have 4 points. Four lines meeting at a point, and you no longer have a region bounded by 4 edges. So you are going to have this situation where there are some exceptional points which contradict that pattern. So you have said it's made into a cylinder. Well, yes, I'm not sure this way of putting it will be it's true that whenever you depict a spherical surface as a rectangle, obviously there is a problem happening at the top because it's a single point which has got represented as a whole line. So there is a problem that way, but what is being shown here is not quite that, because if you replace that problem slightly, instead of saying that at every vertex exactly 4 edges meet, if you said at every vertex 3 edges meet, well, that is possible because you can imagine a cube. You can imagine a skeleton of a cube and then sort of blow it up. So you get a grid with squares around. But the difference between that and the example that I showed is that at every point you'll have 3 squares which meet and not 4 squares. At every vertex, there are 3, every vertex has got degree 3. So it is not really, the problem is not happening because of the connection to a rectangular map. It's a combinatorial difficulty. Okay.
So you can scroll down. There are more questions if you scroll down.
Please. Oh my goodness, I missed them. How does the proof for Euler's theorem and Descartes' theorem work? Now that should be a homework for you, but let me tell you roughly how it's going to happen.
Sir, if you can stop presenting your screen before you go to the board, so we can see you big. You can just stop sharing your screen before you go to the board.
Okay, yeah. Oh yes, I should do that. One minute. 1 minute. There seem to be quite a few questions. Sorry.
Yeah, I will read those out for you if you want.
But the last question, of course, is very interesting. Someone has asked, if I'm not wrong, Euler went blind. He says early in his life, but later in his life, he was completely blind. He lost sight in one eye early in life, and later in life, he lost sight in the other eye as well. But obviously, he must have been a completely incredible kind of a person to operate and do mathematics while completely blind. I should tell you his modus operandi. He used to sit, obviously he couldn't see anything. He had some assistants to whom he would dictate. Those assistants would listen to him, and whenever a diagram had to be drawn, a slate would be brought to him, and just from his own visual memory, he would draw the diagram on the slate. And his assistants would then transcribe that diagram onto the text. So he was absolutely an unbelievable person. All right, let me just show you the connection between the two. I'll just stop sharing. Yes. Yes, I hope you can see.
Yeah, that's good.
It's a very interesting thing. Perhaps we can, I'm not sure how long we can go, but see, it's like this. Let's take some polyhedron. I'll just draw for simplicity something which looks like a cube. Let's say it has V vertices, E edges, F faces. Now, let's say the vertices at I equal to 1 to V, let the angular defect be equal to, let's say, xi. So at vertex number I, the angular defect is xi. So the total angular defect is summation of all such xi's. Now, what is this xi? It is basically 360 degrees minus the sum of all the angles at that vertex. Right? So when you say summation of all this, what does it mean? So 360 degrees, summation of all this. So 360 degrees times the number of vertices. So you get 360 degrees times V minus the sum of all the angles in every face. Okay. Now let's try to figure out what this quantity is. Suppose this edge here, this face here, there's a problem of notation here because there's so many symbols floating around. But you'll have to remember the formula for the total. See, you're adding up all the angles. So you can add up all the angles by going to each face and adding up all the angles of that face. Now remember this result, that if you have a polygon with k sides, then the sum of the angles, what is it equal to? What is the total the count of the, what is it, 180 degrees times k minus 2, right? So that can be written. So this therefore is equal to, so what is that equal to? So if you have to actually write this out in full detail. Oops. So let's see. So you're going face by face, counting the angles on that. So let's say the face number j, let it have, I already called xi. So let's say it has yj edges. So that means the sum of the angles of face j will be equal to 180 degrees times yj minus 2. So that means this quantity here, if you add up all the angles, it will become 360 degrees times v minus this summation of 180 degrees times yi minus 2. Right? Now we have to bring in one more factor now. Each edge, see now what is this yi? You're getting a summation, so we can factor out the 180 degrees here, and you'll get something which is summation yi. Summation yi means what? You're going to each face and counting all the edges around it.
Dr. Shirali, don't use the right corner of the board. It's not visible. The rightmost, the one which you wrote sigma something, 360.
Oh, it's not visible. I'm sorry.
Or the board. Yeah, if you either can shift the board a little bit or shift your the little bit so that it is visible. Yeah, now it's visible. Fine.
Sorry. Okay. Yes. So when you say summation yi, it's like you're going to each face and counting all the edges around it. But then each edge is going to get counted twice because this particular edge will get counted for this face and it will also get counted for this face. So when you say 180 degrees times yi, the summation of yi is just equal to 2 times e. right? So the first part of it, you see, it's that too many symbols so it's equal, you get 360 degrees times V minus 180 degrees times summation yi, but summation yi is just 2 times E, so you get 360 degrees times E. And then 180 degrees times 2 is 360. And how many of them are there? We are going for, this summation is over every face. So you get plus 360 degrees times F. So you notice the last expression is very simple. 360 degrees taken out times V minus E plus F. So the total angular defect turns out to be 360 degrees times V minus E plus F. So if V minus E plus F is 2, then the total angular defect is going to be 720 degrees. If it is 0, then the total angular defect will be 0, and so on. So you can see this connection is very nice connection between them. So, okay, let's come back to the problems. Questions, sorry. 1 minute, I'll go. Where am I now? I'll share the screen again, yes. Yes, one of you have said this. Is the angular defect equal to 360 times? That's exactly what we have just shown. Is Euler's theorem same as Euler's formula? Well, Euler was such a mathematician that there are dozens of results called Euler's theorem and Euler's formula. So some of you may know one very famous one, which is e to the power of pi I equal to -1. That's also called Euler's formula. And there are probably a dozen more of that kind. Can a proof for the fact that 5 or more two-dimensional polygons cannot mute? What's this? Can a proof for the fact that 5 or more two-dimensional polygons cannot mutually share edges arise from these theorems? I'm not absolutely sure I get the question, but if you're you're asking, will this Euler's theorem prove that there are just 5 regular solids, or what are called Platonic solids? This answer is yes. There is exactly 5 ways in which you can construct a completely symmetric polyhedron in which every face is identical to every other face and every vertex has the same connectivity pattern as every other vertex. I can show you that proof if you wish. Do Euler's theorem and Descartes' theorem have application in protein structure? My goodness, I'm not sure I can answer that. Are there applications of the theorem in other fields of mathematics? Yes. Euler's theorem is actually, I should say, as I said earlier, Euler himself, I'll just stop the screen sharing for a moment. Yeah, Euler himself probably viewed his theorem as a geometrical result. It was a theorem about polyhedra, a combinatorial result, but essentially a geometric result. And I should also add that the proof given by Euler is one of the few proofs which later generations of mathematicians have said that it was a flawed proof. He didn't give a completely correct proof. The connection, this kind of a connection which we have shown, was first pointed out by a much later mathematician. I think it was by the great Poincaré. Henri, this French mathematician Poincaré, who noticed that if you drew a network around a sphere, then Euler's result follows very easily on that. So yes, the answer is that this is generally regarded these days as a result about topology, because it's an invariant. It's an invariant about a certain class of objects, and therefore, that's what the kind of thing that is studied in topology. One of you has asked. I'll just share again. 1 minute. What is the probability that two lines will intersect in a circle? Well, we can set about working this out. I don't know the answer to it, but you would have to find a mapping from lines in a circle to some other kind of a region over which you have some handle, because you'll have to decide how you draw those two lines. The basis on which you draw lines in a circle is not that straightforward, but depending on how you do it, you can certainly work out the probability of intersection. You would have to map it to some two-dimensional situation. You'd have to look at, say, two parameters which determine the two lines, and then look at the condition for those two parameters for those two lines to intersect, and then look at the area of that region upon the area of the entire region. We'll have to do it. I don't offhand know the answer to that, but it can be certainly done in that kind of a way. Is there any variance in the theorems when applied to curved polyhedra and polygons? Well, the thing about Euler's theorem is that it's essentially a combinatorial result, which means that it doesn't strictly have to be, absolutely plane faces and so on, plain straight line edges. You can have curved edges. You can have, in fact, a picture drawn on the surface of a sphere where nothing is straight, everything has got curved. And similarly, that example that I showed you about in which there's a cube with a hole drilled through it, you can imagine that to become a donut. So this theorems actually have nothing to do with straight lines or curves, or it is to do with the structure of the space itself. Oh, the last, I see. I think the person who gave that last question has elaborated. I'll read out the question. It is not possible for 5 two-dimensional regions to mutually share edges. Okay, you're thinking in terms of the 4-color theorem. To my understanding, the 4-color theorem is much more complicated than can be reached by these arguments. There is no easy proof of the 4-color theorem, and some of you may know that the 4-color theorem actually ended up taking well over a century to get proved. So I don't think Euler's theorem will get you the proof. Of course, it is a required ingredient, but it's not enough. Very much more is required than Euler's theorem to prove the 4-color theorem. But Euler's theorem can be used to show many such things. For example, you can show, I'll just stop again. You can show, for example, let's say you have 5 points and you want to join all of them by a line, which could be straight or curved. So I've connected this to all 4, then this. Now I want to connect to this here. Then I want to connect it to this. Okay. Then this is left. I join this. Unfortunately, now I am unable to connect this to this without going through this, without creating an intersection. So can you prove that kind of a result using Euler's theorem? Well, you can. And you can do it like this. Here you have 5 points. So V is equal to 5. Every 2 of them are supposed to be connected. So that means E is going to be 5 choose 2, or 5 choose 2, some more commonly written like that, which is of course 10. So therefore, what is F equal to? So since V minus E plus F is equal to 2, so F should be equal to 7. 10 minus 5 plus 2, F should be equal to 7. Now, if you look at these faces very carefully, for example, let's look at this face here. The number of edges around it is 3. Right? Similarly, if you look at this face here, 1, 2, 3. You can't have a face with less than 3 edges. So if you go to each face in turn, face by face by face, and count the number of edges around each face, then the number of edges that you get, since each face has got at least 3, you will get a count of at least 21. Right? You can't get less than 21. But on the other hand, every edge is going to get counted exactly twice. There are 10 edges. Every edge is shared by only 2 faces. So you should actually get a count of 20. And according to this argument, you will get a count of at least 21. So this argument shows you that it is not possible to have this configuration at all. So the answer to your question is yes. It is possible to use Euler's theorem to establish certain results of this kind, but the four-color theorem, no. Four-color theorem is far too complicated for this. There is no easy proof which has been found for the four-color theorem. That's a long story, which I don't think we can go into right now. Well, I'll share this again, but I think we have covered everything now. Oh, some more have appeared. Does a parallel to the four-color theorem exist in 3 dimensions? Oh, what I thought. Suddenly this thing vanished. Okay, it has reappeared. I hope, is it visible to everyone, Anand?
Yes, sir. Yes, sir.
It suddenly vanished from my computer, but reappeared. Does a parallel to the four-color theorem exist in 3 dimensions? I'm sorry, I don't know the answer to that question. I don't believe there is any parallel of that kind. Because what do we mean? You want to draw a map in 3 dimensions. You see, the four-color theorem is basically about what are known as planar graphs, planar networks, right? And the fact that there are certain I lost you. Are we together?
Yes, sir. Yes, sir. We just lost you for a bit.
Yeah, I don't know. It mysteriously vanished. But maybe I don't have that much now to add. Let me just. Yeah. Okay, the last question. Okay, I'll share the last, and maybe we could perhaps take a pause after that. So the last question, it says, if we can say that a figure with a hole will have an Euler's value of 0, well, I'm not sure you can put it like that. What happens is, if you have an object which with a hole, then the Euler's characteristic goes down, and if you have more than one hole, the Euler's characteristic goes down still further. Okay, so it's not that. It's true, yes. If the value is 0, then it does mean that that object is not like a sphere. It will have a hole, but it may have more than one hole if this value is less than 0. Well, so if you're saying that if the Euler's characteristic is 0, then it has a hole, yes, that is true. That's a true statement. Anand, perhaps we can.
Yes, sir.
I can't see anything else. I'm not sure I can add anything further to these questions.
Okay.
All
okay,
right.
Sir. Okay, Mani sir, shall we wind up?
Mute myself and.
Yeah.
Thank you, Dr. Shirali, for such a wonderful talk. And I'm very happy that many questions had come up showing the interest in mathematics by students. It's very encouraging to see that. Thanks again.
Thank you very much for this opportunity.
All right. Goodbye for now, all of you. I'll say goodbye now.